Hi, I'm Fabian. I'm going to talk about Miris, a system we built for efficiently executing object track queries over large video datasets. Today, cameras collect a large amount of video of very diverse scenes. We believe that if we can efficiently perform video analytics tasks on large video datasets, we can benefit a wide range of applications. For example, analyzing traffic camera video could offer insights that can better inform traffic planning decisions. There has been much work in executing queries that involve machine learning models over the last few years. Broadly, these works focus on answering detection and counting queries, like the query here to find video frames with at least 3 buses. However, many analytics tasks are object track queries that we found prior work did not effectively address. So what's an object track query? Well, an object track is the trajectory of an object over the segment of video in which the object is visible in the camera frame. So here's an example of the track of a van. It's just the sequence of positions where the van appears in the video. An object track query is a query that applies some predicate on object tracks. For example, we might be interested in cars that turn right through this junction. In that case, we could draw 2 boxes and select object tracks that start in the red box and end in the orange box. Conceptually, to execute this query, we would compute all object tracks and select the subset that satisfy the predicate. Many video analytics tasks can be expressed as object track queries. Some queries may involve object speeds. A user interested in finding cars that brake rapidly at a junction may formulate a query that selects tracks with a sharp deceleration. Other queries may involve the positions of multiple objects. In this video captured of a river, we may want to find interesting events like when a bear catches a salmon. To do so, we could look for pairs of bear and salmon that intersect for several seconds. Similarly, to find cars that run a red light, we could look for cars that drive straight through a junction in a particular direction while the traffic light controlling that direction is red. A naive way to execute these queries is to first apply an object detector on every video frame. In this case, object detection yields bounding boxes of cars shown in yellow. Then we apply an object tracker to associate detections of the same object across different frames. On the right, the colors indicate different tracked objects. Once we have the object tracks, we can just select the subset of tracks that satisfy the query predicate. The issue is that the object detector is expensive, and executing it on every frame is costly. Executing a query in this way over 1 month of video captured from 100 cameras would cost $72,000 to process on AWS. Rather than apply the object detector on every frame, we could try applying it at a lower frame rate where frames are temporally further apart. So we could apply it at 1 frame per second, or even 0.5 frames per second. The challenge then becomes accurately computing object tracks and evaluating the predicate at those low frame rates. There are 2 main issues that we find may arise when tracking at low frame rates. The first issue is quite simple. Sometimes the tracker model makes mistakes. Here are 2 images 2 seconds apart in a video sequence, and the orange car and green car are actually the same car. But the tracker, when it inputs these 2 frames, says there's 0.38 probability that the orange car matches the green car, but 0.42 probability that it matches this other car along the red line. So the tracker actually gets it wrong. It outputs a higher probability for the wrong edge, and we need some way of correcting these matching errors. Another issue is errors when evaluating a predicate over tracks sampled at low frame rates. Suppose we want to find cars that go from the green box to the orange box. And here's a track of a bus that we see first in the top right, then in the middle of the junction, but then it's gone and we never see it in the orange box. At the full frame rate, the bus would pass the orange box, but because we're looking at frames 1 second apart, the query engine might think that this bus actually does not satisfy the predicate, even though it does. We developed Miris to address challenges in efficiently executing object track queries. There are 2 key ideas. First, to address the tracker error and predicate evaluation issues that I just detailed, we propose tracking at a low frame rate, but then having a way to decide when we need to sample frames at higher frame rates to avoid those problems. The second idea is to incorporate query planning into the object tracker. We developed a 4-stage object tracker. The stages are tracking, filtering, uncertainty resolution, and refinement, and each stage exposes a number of parameters that can be tuned to optimize execution for a particular query. Then a query planner automatically selects these parameters given a query. I'm going to first summarize each of these 4 stages, and then briefly discuss the planning process. The first stage is initial tracking, where we track at some initial low frame rate, and that frame rate is actually a parameter. To track objects, we first apply an off-the-shelf object detector, YOLO v3, on all sampled frames. We then apply a novel tracker model that we propose, which incorporates a graph neural network, on pairs of consecutive frames. I'm going to gloss over the details of our tracker model for this talk, but to summarize, it gives us the probability that each detection in the first frame matches with each detection in the second frame. So we repeat this on all pairs of consecutive frames that we sampled from the video. The output of initial tracking is a graph like this. All of the blue circles are object detections, and each column of circles are the detections from one video frame. So for example, this red column consists of detections at the frame 12 seconds into the video. Edges connect detections of the same object. So this sequence of detections at the bottom is actually just an object track. What's special about our approach is that in the graph we sometimes output multiple outgoing edges at one detection. We want this to happen when we have situations like this, which we described earlier, where the tracker outputs a higher probability on the wrong edge. We find that oftentimes when the tracker makes a mistake like this, the correct edge doesn't have the highest probability, but its probability is still close to the highest probability. So in our approach, if the probability of some outgoing edge from the orange detection is close to the highest probability of an outgoing edge, that's 0.42 here, then we keep the other edge as well, and we may potentially keep multiple other edges. What we mean by close is going to be controlled by a parameter. And so when this happens, we get these redundant edges. They can't all be correct, since the detection should only match to one detection in the next frame, but we keep them around for now because we're not sure which edges are correct and which are wrong. The next stage is filtering. In the third and fourth stages, we're going to be sampling frames at higher frame rates to address either redundant edges, which is related to the tracker error issue, or predicate evaluation issues. Filtering reduces the workload of those later stages by pruning tracks that we are confident will not satisfy the query predicate. And if the filter is confident that a track will not satisfy the predicate, then we discard the track and do not process it further. The next stage is uncertainty resolution. This stage addresses the redundant orange edges that we added during tracking when the tracker model outputted high probabilities along two or more edges. It tries to determine which edges are correct and which were wrong. For each group of redundant edges like this, we sample the frame halfway between the problematic frames, so here we sample the frame at 15 seconds. We run the object detector on this frame, and then we apply the tracker model to match detections both between the frames at 14 and 15 seconds and between the frames at 15 and 16 seconds. Since we're now applying the tracker on pairs of frames that are closer together in time, we hope that the tracker model makes more accurate tracking decisions and outputs a higher confidence. Here, after processing the extra frame, we no longer have any redundant edges, but in some cases we may need to recursively apply this procedure if the confidence is still low, and so we might process the frame at 14.5 seconds. Like uncertainty resolution, refinement also samples additional video frames. But whereas uncertainty resolution addresses tracker errors, refinement addresses cases where we cannot accurately evaluate the predicate due to the low sampling frame rate. I'm going to skip over this stage, but the details are in the paper. Okay, so that's how our object tracking method works. Now I'll briefly discuss the query planning process. So suppose we have a video dataset like this, along with some query. In addition to specifying the query, the user also specifies an acceptable accuracy bound. So the user may say they want query outputs to be, say, 99% accurate. Our query planner borrows techniques from approximate query processing. Overall, we will randomly sample a subset of video and independently set each of several parameters for our tracking method to get the highest performance under the accuracy bound in that sampled subset. So we first randomly sample a few segments of video, and in each segment, we apply the object detector and tracker at the full video frame rate to derive accurate object tracks. And we evaluate the predicate over these tracks so we know which ones should appear in the query outputs over those segments. The query planner uses this as validation data to tune tracker parameters. We independently set parameters for the filtering, uncertainty resolution, and refinement stages. Initial tracking and uncertainty resolution expose a single parameter that can be tuned to derive a speed accuracy trade-off. So we set the parameters independently in those stages such that the tracker would correctly recover 99% of the tracks in the sampled validation segments. And we can verify this since we've already captured those tracks at the full frame rate in those segments. Filtering and refinement each expose several methods that the planner must choose from, and each method has a single threshold that again offers a speed accuracy trade-off. For those stages, we compute thresholds for each method or combinations of methods to recover 99% of the tracks accurately, and then we choose the method or the combination that has the highest speed. Although selecting a combination of methods based on the performance of each combination on the validation data weakens the probabilistic guarantee from the random sampling that we did, there are few enough combinations that we need to test that we can still expect that when executing the chosen query plan over the rest of the video, it will perform similarly to its performance in the validation data. We evaluated Miris on a diverse dataset consisting of 9 queries involving 5 distinct video sources. The queries include some of the ones we discussed earlier, like finding cars that run red lights and identifying instances of hard braking. We compared against 4 baselines. Overlap-based tracking uses intersectional reunion scores to match detections between pairs of consecutive frames. KCF uses kernel correlation filters to update the position of detections based on visual cues. FlowNet applies a neural network model to compute optical flow and uses that flow to match detections. And probabilistic predicates uses overlap-based tracking, but applies an approximate classifier to skip segments of video where the classifier is confident that there are no tracks that satisfy the query. We also compare against GNN, where we apply our machine learning model that incorporates a graph neural network to match detections, but do not use the rest of our approach. We evaluate the methods in terms of speed accuracy curves. Accuracy on the x-axis is measured in terms of an F1 score comparing the tracks output by each method to ground truth tracks corresponding to each query that we hand label. Speed up is on the y-axis. So ideally, we want to be further up and to the right. Here are results on the first query. Our method in maroon provides a 15-fold speedup over the best baseline at the highest accuracy levels on the right of the graph. And here are the full results on all of the queries. As you can see, Miris consistently outperforms the baselines, yielding a 9-fold average speedup. By comparing the maroon and green lines to the baselines, we can see how much speedup comes from the tracker model and how much comes from filtering, uncertainty resolution, and refinement. On queries 3, 4, 6, 7, and 8, the tracker model, the green line, alone performs quite poorly, and these other stages, including incorporating the query planner, are needed to get good performance in the maroon line. In conclusion, Miris is an approach for efficiently executing object track queries on large video datasets, and it promises to greatly increase the complexity of video analytics tasks that we can perform at scale, moving from predominantly image-level queries considered in prior work to these queries that we've looked at that reason about object tracks.